In this case study, we're going to look at this problem of a simple mass spring damper suspended by a roller that is released from the top of this rail. And so the roller it's a hard roller. It's just going to come down this guided path. There is gravity here, bringing this down. So what we're interested in is we're going to assume that this is a model of a system that we're interested in the path of this mass. It can't swing, it can only move vertically and of course horizontally as the roller moves down this rail. We might be interested in, say, what's the peak deflection, the oscillation that the mass will go through, and also like what kind of contact forces do we have here. So say you could make selections on the type of roller you might need that could possibly go, say, into wear studies if this was some kind of a process in some kind of environment that, say, is carrying loads in a very repetitive manner. So you have some parameters here to work with. There's a length of the rail here that's given as 1 meter. This angle might be something we could also play with, this height. And the stiffness and damping and the mass are given. This is a good example where if you took the time, you could actually solve for the response of the mass, say, analytically, but it would be much more time consuming than even setting up the simulation as I'm going to show here. As I mentioned, the rigid roller moves down the incline and there's suspension mass. The suspended mass is going to be forced into some oscillations. This is a problem also where we can model it by, if I know the motion of this point here, then the model for the suspended mass is not too difficult. So this is a problem where if we can determine that input z of t in terms of velocity and displacement, we can use that as an input into the system and then use that in our simulation. So we're going to assume that the roller motion can be determined analytically and then used to define the motion of the base, and also that the roller begins right at the top here. And then from there we can solve for the rest of the motion using a simulation. So how do you go about finding that roller motion as a defined input? Well, let's go ahead and concentrate all the mass at the roller. And then this can be treated as just a particle falling down this rail. We'll do a free body diagram here, and you can see that if you focus at the motion along the rail here, it's some known angle theta. Simply, you can show that the acceleration or the rate of change of the velocity or x double dot is just g sine theta. So we have a constant acceleration down that path. Note that the key assumption here is that there's very low friction, right? Low to the point of being negligible. So that's why we get this constant acceleration. So we now have, and so actually I'm working out the mass times the velocity, the acceleration along the path is just the mg sine theta. And so I can integrate and I can find here that the velocity over time is a constant. Sorry, velocity over time has a constant rate times time. This means that I can solve for the velocity in the vertical direction, which is the one that I want, or the rate of change of the displacement, by just taking the component in the vertical direction. And so I basically have now the velocity of the roller in the vertical direction. Prove to yourself that this expression is true. So now we can move on and use this as an input to the rest of our model. First, now that we have the roller motion being well defined, it should be relatively easy to find both the velocity and the position functions as inputs for the model. Right, a little typo there. So we're moving along this rail. Now you can solve for the position by just integrating again. The reason that that's important is because, right, when you think about the roller moving along the rail here, you want to know when it's on this path versus when it's on this path. So you can integrate and find the time after release that it reaches the end here. So if you integrate the position along time, you know that it reaches a distance L at some n time t sub e, and that occurs at 1/2 g sine theta t squared. That means you can solve for the time, call it t sub e, when it reaches the end of the inclined rail. And that's important because you want to split the inputs, right, over time intervals, right? So now the roller motion is defined over 2 time intervals, one when the roller is on the incline and one when the roller is flat. Okay, and that means now that you can run the simulation up to some time t sub e, and when the roller reaches the end, and that's when the vertical velocity is, as we just found. But once it reaches this region here for t greater than t sub e, right, then the roller vertical direction goes to 0. So those conditional statements have to be used when you're defining your input into the model that we're going to build for the mass spring damper system. The other reason that this is important, if you think about the contact force on the rail when you're in the incline here, right? If you think about it, that the vertical force is in this direction applied by the suspension. The contact force is going to be at an angle. When it's in this direction, the full contact force, right, is vertical. So it's less when it's along the incline, and I'll show you how you can implement that as well. So these types of changes and conditional statements can be put in the system function file, as I'll show shortly. Now for the model of the mass spring damper system, we have now a model for this input as a velocity. I should put that z dot t, but also as a position coming down. So we know the base excitation here, and now we just look at a free body diagram of that mass. We have the spring force, the damping force, gravitational force. We want to look at the equation for the motion of that mass. So that's mv dot m, the vertical direction, is minus fk minus fb plus mg. The force fk and fb are as defined here, right? Remember, the spring force is z sub m minus the zt, and these are inputs, right? Known inputs. So this one equation then, when you substitute these expressions in here, takes this form. This is the vertical acceleration of this mass. Again, that's an input, and so is this here. We're actually going to treat this here as a variable, as I'll show you shortly. So the other equation that we want to add here is we want to find the position of this mass, and we can do that just by defining a new equation, z dot m, which is just the velocity, v sub m. See, this equation will help you find v sub m, which is a state, but then you can define a new state, zm. So we're building up a little state vector here, right? The first one is vm. Now we have zm. And then we also want to track the roller position, zt. So since we have z dot t, remember this is what we solve, the right hand side here is what we solve for analytically. We can define another state, z sub t, and then it's a state in here and we're solving for it. We can put it right in there since we know v of t as an input. So we're going to be able to find the position of the rail and use that as an input. We don't, we haven't actually defined it yet, but we could define the spring deflection also. And that is simply the difference between, the velocity Vm minus the input velocity here, v of t. And remember, this is an input, so this is actually a fourth state equation that we wanted to have these. And all of these then can be solved for through a simulation. Now, before we go into looking at that simulation setup, we've identified 4 different state equations, so we need 4 initial conditions. Okay. Since the track begins at 0, we'll take zt of 0 to be 0. We're also going to go ahead and say that initially the mass is not moving, so that's an easy one. V of m at time 0 is 0. Now, what is the initial mass position? Well, we know it's hanging from the rail. So we want to find where is this mass relative to that, and that's going to have some deflection due to the weight. So the way we can find that is by going into the original differential equation for v dot m, setting that equal to 0, because we're going to say that initially at time equal to 0, the acceleration is 0. That's the equilibrium relation. Plug in all the known variables and parameters, and at the end of the day you can end up with a relationship for the initial position of the mass at time 0 in terms of the mass, gravity, and the stiffness. Finally, the initial spring deflection can also be found because we're going to assume that that's the same as the mass position, right? Deflecting from some non-loaded position to a loaded position based on applying the weight of the mass onto the suspension. So that sets up our 4 initial conditions that we need for our 4 state equations. Now, we talked about initial conditions. We want to talk about other calculations we want to make, and one of them is the contact force. And if you think about it, with the roller on this rail, it's got this suspension on here with the spring and damper and the mass. That force here is basically the sum, right, of the spring force and the damping force. So when now it's at an angle, right, and this angle here is theta, you can show then that the contact force, right, perpendicular to the surface of the rail will be fk plus fb cosine theta. When it gets to the flat, region, you'll have the full spring damper force pulling down. And so remember when we talked about when you're in the inclined region, you have a certain input, and when you have on the flat region, so you need to use two different contact calculations depending on where you are, where the rail is, where the roller is on the rail. Now, initial conditions, auxiliary calculations, let's see how we put that all into a simulation file. So here's our standard function file. I've got the output relations here in y and the state derivatives, and here's mass track is the name of this file. I've got global definitions, and then I'm defining each of my state variables coming in through this state vector, right? Remember, x contains the 4 values, and here I just assigned them physical variable names so I can use them in my calculations. Here is the first conditional based on T sub E, and T sub E will need to be determined prior to coming into here in the simulation file. Well, if I know that I am at a time less than T sub E, then I can calculate the velocity based on, right, the vertical acceleration on the incline, as we found initially. And also the contact angle, which I'm calling CA, is cosine theta. So when I calculate my contact force, I just need Fk plus Fb times that contact angle calculation. Now, if I'm on the flat, then, in other words, I'm not less than T sub E, I'm greater than T sub E, then, oh, the vertical velocity is now 0, and the contact angle becomes 1, so I have the full suspension force giving me my contact force. So this conditional statement here serves two purposes in the way it's written. Once I have these in, two relations that I can calculate here, I can go through and calculate my damping force, my stiffness. Here's my contact force. That depends on contact angle. And then I put all that into my 4 state equations, here, as I've written before. And then I define my state vector. Two possible outputs that I might want to also look at are the contact force and the vertical velocity, which is not a state. So I put it into my output variable so that I can pull them out of here after I run my simulation. Finally, as before, simulation file sets up all the parameters, angle of the incline, and all the mass, damping, stiffness parameters as shown before. Here's my calculation of T sub E. Set initial conditions as we defined already, and run RK4 fixed. Then I go through and compute my output variables. Finally, plotting. So as you can see, all this hopefully is becoming standard. And you can see that I use the same pattern for all of these. Finally, looking at the simulation results, I'm plotting on this top graph here the rail position as I move over time, and also the position of the masses in green. By the way, we know that the rail, as I move forward in time, right, is a defined motion, but in the mass falls, right, it should be below it, right, but I've plotted them together. You can see then that there's a sort of a peak kind of overshoot of the mass, and this might be a key parameter that you want to look at in terms of how the mass responds. Also, the other thing is you might want to know how long does it take for it to settle out and stop oscillating. Contact force is also important. Look at as soon as it hits the flat region, which is what happens here, you can see there's a big peak that occurs there, and then the oscillation. Okay, so this just shows typical output from that type of simulation for the output variables that we selected, contact, as well as for states and defined in the system model.